Hello, welcome to the 11th tutorial. This one will mostly be on calculus. If you are not a calculus student, do not worry. There will not be anything here that you have to see before going on to future tutorials. However, I would encourage you to listen to the first section, which will talk about piecewise defined functions. After that, you can skip through it, but you may also be interested in one of the subsections under derivatives with a little bit of graphics work. For the calculus folks, we'll talk about limits, derivatives, integrals, series, and differential equations. All right, first of all, let's go back to piecewise defined functions. Piecewise, then I have one piece here. Here's the function and my condition inside curly braces, comma. Here's my second piece, another function and the condition within curly brackets. Then both of those are within one set of curly brackets, and then I close that off with the square bracket. Now, when I just ask for f of x, you'll see what comes back. This is in more traditional notation, but I do have the 0 and true down here that Wolfram language kind of threw in. You just need to be used to seeing that. All right, if I would like to enter this in a much more traditional way, I can use keystrokes. Escape PW, escape, will get me the brackets on the left, and then Control Enter will get me the 4 pieces, and if I need more pieces for more conditions, then I can just hit Control Enter again. All right, now let's look at a graph of this. It's very nice. It does not put a connector in here, which of course is not supposed to be there, but you also don't see which side the equality is on. All right, let's come down and look at limits. All right, couple examples here. My sine of x over x as x goes to 0, that notation shouldn't be a surprise. I can put it, x goes to infinity in here. I can use keystrokes, I can use the palette, or I can simply type infinity. Now, let's go back to our f and look at that again for a moment. From the left, where we usually use the notation x approaches a with then a little minus sign, this is going to 1. And from the right, it comes down to 0. Mathematica in the last couple of versions has changed this direction arrow, and in quotation marks because I'm just putting plain old words in, but from above I get 0, and from below, and there shouldn't be any ambiguity there as to what those words or what those expressions are telling me. Now, if I do not specify a direction and just say x goes to 1, the Wolfram language knows that the limit does not exist, and it just spits back indeterminate, as it should. Clear F, we'll get rid of that for the moment. Okay, another form for derivative, just another example. Derivative of tangent, and by definition as h goes to 0, I get secant squared. I can certainly put this in traditional form and get my square where I'd like to see it, but hopefully you're comfortable with reading that at this point. Okay, on to derivatives. This is one of the few places where Mathematica does not expect the entire English word. Just a capital D. Here's my function, comma, with respect to x. And that is natural log of x, recall. I can put in a generic f and g so that I will see quotient rule. If I want, I can change the form by simplify or together to put that with the common denominator into a more familiar form. I can also use other letters in here. That's part of why I need to say that the derivative is with respect to t. And if I want a higher order derivative, I use different notation at the end. Here, I'm asking for the third derivative, but this certainly works for other numbers as well. Inside the curly braces, x comma 3 will give me directly the third derivative. Now, on the other hand, cute little function, sine of x. Input that, f prime of x gives me the derivative, and f double prime, second derivative, and I can continue as I wish. If I want to use the classroom assistant palette, you're looking for that notation. That goes along with the multivariable notation, but I put my x down here, derivative with respect to x, and then just put my function in. And in fact, if I am doing multivariable work, I can take a second derivative, second partial in this case, with x and then with respect to y, but use that notation as you need to. Okay, piecewise again. All right, I'm going to clear this and just re-enter it just so it's right in front of us one more time. I can use f prime of x, and it will give me good format here with this little thing down there. Please note that I did lose the equality up here, as I should have. When x equals 1, f prime of 1, also indeterminate. Okay, so the Wolfram language can figure out a lot of that stuff for you. Clearing f, good habit. Implicitly defined functions. All right, here I'm going to do this in a slightly more efficient manner. I'm going to give a name to my equation, but my equation is that. All right, I have a single equal here because I'm naming it, and a double equals here as part of my equation. Now, I can't take the derivative just of this thing with respect to x because there are a bunch of y's in there. So I'm going to take my equation, and every time I see a y, I'm going to substitute f of x. Now they're all x's, and I can take the derivative of that output with respect to x. Okay, but that's still not quite the end. Then I want to solve that output and solve it for f prime of x. And there I get my derivative in a much more convenient form. All right, another example here of a typical max-min problem in calculus. And for those of you who are non-calculus students, this may be interesting just to see the work with graphics. All right, so we're going to take a curve y equals cosine of x from minus pi over 2 to pi over 2, just the one arch, and then find a rectangle that can be constructed in that with two vertices on the x-axis and then the other two vertices going straight up and being on the graph of the function. All right, so let's plot this so we can understand our problem a little bit better. What I'm looking for is the rectangle with the maximum area. Now, this is new, but we will come back to this in more detail in a later tutorial. Rectangle, I'm naming my rectangle. It's going to be magenta because that's pretty. And I have a rectangle that goes from minus 1.10, so about down here, up to 1.1 comma cosine of that. So I'm getting the two opposite vertices of my rectangle. I'm creating that rectangle, and the Wolfram language does assume that my rectangle is, in this case, because I haven't stated anything else, it's assuming that it's just a horizontal and vertical and nothing on a slant. And then I'm going to show my rectangle and my graph and put in some axes. All right, so from here, I could have a rectangle that is much wider and shorter, or I could have a tall and skinny rectangle. And the idea is to find the rectangle of maximum area. So I'm going to define my area of rectangle, 2x. Okay, that's my x value there. So my base is 2x, and then times the height, which will be cosine of x. All right, now, a couple different methods for doing this. Find root, we talked about that earlier. I've got trig in this and non-trig algebraic piece too, so I better use find root for solving this. Here's my derivative of this function equals 0, and a guess starting at x equals 1. And then I get an x value. Well, if I take the area of my rectangle, here's my function, and substitute for x, my 0.86 stuff, then I will find the area I'm interested in. Now, you know, there's more that's built in. There's a find maximum command. Here's my function, and I need to give an initial guess. 1, good enough. And there's the same information. It gave me the area of the rectangle and the x value also, kind of quickly and directly, but we know studying calculus is good. All right, onward, integrals. Integrate. Here's my function, and with respect to x, and I will get the antiderivative. Some of these become much more interesting here. Some I don't really want to deal with, but that's okay. Wolfram language can handle a lot of these. To do this with keystrokes, escape, int, escape, and to get the special d that goes with the dx or whatever variable I am using, escape, dd, escape. All right, so I can write this in, but of course, there are some that just cannot be done mathematically. And so it just kind of spits that back at you. Here's another little example if you would like that. Well, that gave you a name, but it still didn't really do much that most first-year calculus students would be particularly interested in. Okay, if I would like a definite integral, escape, din, tt. Okay, and then escape again will give me the formatting for definite integral and substitute things as I wish. On the other hand, I can do an integral here, and x goes from 3 to 5. That's my basic syntax for domain. Or I can do n integrate, same function, same region. That's okay. All right. Please note that this is more efficient than taking integrate and then putting a numerical in front of it, because what that means, if I do the integral first and then put the n in square brackets around that, it will try to do the exact integral first. And so sometimes that will just be slower. Depends what you're doing and how complicated it is. Improper integrals, no problem. And I can also plot integrals. Here I'm going from 0 to x, and then I have t's over here. I do not want the same variable used in 2 different places within my integral, but I'm plotting this as a function of x from 0 to 2 pi, and this does take a little while, and sometimes I get some things that I really don't like and some warnings about it, but sometimes it's very cooperative. Well, the antiderivative of cosine should be the sine function, and especially going through 0, 0. Okay, series. Series, oh, surprise. Here's my function, and x, I'm centering it at 0, so I'm looking at Maclaurin series in this case, and I want the 6th order series. And so I get the function, and then I get this little thing at the end. That's to talk about my error or remainder. If I want to be able to plot this, I don't want that there. I do normal of, in this case, I can do it with my last output, and it just takes that extra little piece off. Or you can just put normal around the command series to get that more efficiently. You don't have to do it in 2 steps. Okay. We can find a couple others if you'd like. Differential equations. Okay, now I need to tell Mathematica what variable I'm using in here, and so I don't want just y's and t's floating around, that I need to say that y is a function of t, just as I did with implicit derivatives. Okay, so y double prime of t minus y prime of t minus 6y of t equals, double equals, t. And then y of t is my dependent function and t is my independent variable. Okay, and in this case it's 2nd order, so I get a C1 and a C2. I can certainly do put in some specific conditions. There is lots more that one can do with differential equations, but we'll just go there right now. I encourage you to look at the help system for much more information. All right, down to exercises here. All right, let's look at this. Piecewise defined function. Well, I've entered this, but now we need to type it in again because it's good practice. So G, and I want X underscore, close that, colon equals, then I'm going to use escape, PW, escape to get my curly brace, and I'm going to use control enter to get 4 pieces in there. Okay, so I want 1 over, for that piece, I want 1 divided by x plus 2 quantity squared, and tab over to the next piece. I want that for x less than negative 2, tab again, and I want 1 when x equals negative 2. And then I need to add another row in there, so control enter again, and in this case x squared. My functions are not exciting, but they let you see what's going on here, and for x greater than negative 2. Okay, so I want to enter that first of all. I'm going to come down here and plot the function. So g of x, and let me go from, let's say x equals negative 4 up to 3. Good enough. Okay. Now, in this case, you don't see the 1 in there. So there is supposed to be a dot there. Won't show you that. But in fact, Mathematica does really understand that it's there. So I want to evaluate this at a few places just for the heck of it. G of negative 3, for example. Yeah, that's 1, okay? Because if I put a negative 3 in there and square it, square the x plus 2 squared, I will get 1. Let me change that to negative 4. Yeah, it knows what's going on here. If I do put in g of negative 2, I do get 1 out as defined. If I put g of negative 1 in, we're back up to 1 here. Okay, so it can handle all of this when I'm evaluating things, but you do have to watch out for the graph a little bit. Okay, now a couple of one-sided limits. So limit, I want g of x as x approaches negative 2. We'll do that first. Indeterminate, yep. Okay, then I'm going to take, well, I'll come down and do this the cheap way so I don't even have to type again. It's actually more efficient. It's not cheap. If I do insert input from above, type that again, and then let me put in here direction, and from above, I don't even have to type that stuff out. I get 4, that's where we were coming in here, and keystrokes this time. Same command, but this time I'm going to get rid of that, and from below, put that in, and infinity as we see the graph going off to positive infinity. Derivative. Okay, so derivative of g of x with respect to x. And I get these pieces. The quality doesn't show in here anywhere, but then it's just kind of losing that other piece. Yep, there's an indeterminate spot. That's true. Okay. And if I want a definite integral here, well, negative 2 is my problematic piece, but that's only at 1 point. So let's just take, well, let's do this by keystrokes. Escape, int, escape, and I want g of x, and then I need the special d, so escape, dd, escape, x, we'll put that in there. Oops, that says definite integral. That's indefinite integral. Okay, it's got my pieces in there. So let me do, sorry about that, got to read the instructions, huh? Escape, dint, And now come back, move that cursor so it's there, -2 tab 3 tab g of x, and tab over and put x in, and 35/3. Okay, that is a very, very quick introduction to a lot of calculus that can be done. Again, you are encouraged to use the documentation center and learn a lot more about the fine points of these commands. Thank you very much.